Hello friends, my name is Mehmet. In this tutorial I'm going to talk about the autofrettage process. The autofrettage process is a work hardening process as a result of applied enormous pressure. In order to do this process, I select a geometry which has the inner diameter is 3 mm, the outer diameter is 7 mm. It is a tube and the length of this tube is 35 mm. These dimensions are taken from in the application of water jet process because you know the water jet cutting machine is working under very high pressurized liquid water, and this liquid is pressurized with hydraulic pumps around this pressure is around 500 megapascal, even higher, and conveying this liquid by a tube, and this tube has the dimensions around this value. Therefore I selected these dimensions. Let's start to drawing this tube on my FEA software. Geometry and mesh, cylinder, add cylinder. First of all, I will specify the center of this cylinder on this grid. The center point is 0, 0, 0. Specifies this point. Let's write 0, 0, 0. And the second coordinate is the length of my tube, 0, 0, 0, not third coordinate is 0, it should be 35 millimeter. X, Y and Z. This means that our tube has the length 35 millimeters. Enter. The radius of this tube is 35 millimeter the outer, and again 35 millimeters the outer, because our tube is a cylindrical geometry and not a conical. Therefore the first and the second diameters are equal. Let's add the second cylinder, which will create a hollow tube. Again the origin is 0, 0, 0. This is the beginning point, and 0, 0, 35. And the radius of this cylinder is 1.5 millimeters. Now we have two solids, and by applying a subtraction process, now we can obtain a tube. Okay, the second step is the generating meshes. Mesh resolution is 0.4, let's say. Let's look at. Not so. Maybe this will be higher resolution. Yeah, okay. I will not use a refinement box. Okay. We generate the tetra elements. Number of elements is 204 20,000 elements. The second state is the material definition. A standard material. This properties is stainless steel 304 approximately, and the Young modulus is 210 gigapascal. Poison ratio is 0.33, and we have to define the plasticity properties. Let's look at our plasticity properties. In order to see the work hardening effects, we have to define the yield strength and work hardening properties. And in this tutorial, I will use a Bilinear work hardening properties, and I also have Bilinear stress strain curve. The yield strength is 872 megapascal, and work hardening SUT is 890 megapascal. This can also called as a tangent modulus. The tangent modulus is going to be calculated stress over strain differences as like this, as like calculation of elastic modulus, and the work hardening stress must be higher than yield strength. To define these parameters, I will create a table. I'm going table tab. Our property is equivalent plastic strain, and yield strength is 872 megapascal. This is the elongation. This is 872. This is the horizontal, which means strain, and this blanks are representing the vertical axis, which means stress. Okay, let's define the work hardening curve, and the minimum should be, to make the selection easier, I will write this value 890. Okay, add points. This is the first point, this is the second point. This is my work hardening curve. Okay, let's collect the material properties, plasticity, activate the plasticity, and yield strength is representing what this work hardening table. The von Mises yield criterion will be used, and other criterions are also available in this session. Okay, let's define this material to our solid body. Is there anything which I missed? I think no. Let's continue. We define the material. Let's define the boundary conditions. First of all, I will apply a fixed boundary condition from the nodes. Let's look at the vertical line. I will hold from these nodes. Let's look at, did I select 4 nodes? I select one more. Okay. Apply the selections. I fixed my cylinder from this point. I cannot fix for the circumferential edge, because when I apply the pressure, our cylinder will expand. If I define the fixed boundary condition from the circumferential edges, this boundary condition will not allow for expanding. Therefore, higher hydrostatic pressure will be encountered. Okay, this is now we will apply the pressure inside of this. In order to see the effects of the pressure in terms of the residual stress or plastic deformation, I will apply and release the pressure in a period of time. There is a figure here. I will not use the exact of this time scale, but I will use this pressure magnitudes. It will start from 0 to 760 megapascal, and then I will release gradually to the initial condition. In order to make this, I will define a table again. This is a timetable. From 0 to 1, it's okay for me. Of 0, 1, and 0, releasing the pressure. Okay, and define phase load, pressure 760 megapascal. Yep, and my table is this. At which phase? This phase. It should be solid phase. Okay, and let's okay. Is there anything we missed? I think yes. We have to define the contact deformable. This is our deformable geometry. Okay. We have to define this, otherwise our finite element software will not solve, because we have to define the property of this solid shape. Is it rigid or deformable? Okay, the step is defining the load cases. There is no contact table, and total load time is 1 second, and our step is 50 steps. Okay, and defining the job. Let's define the large strain enabled. Defining the load case. This load case will be solved in this solution. Now we will select the job results. We will investigate the one-method stresses and other stress components, but another things. auto strain, plastic strain, and check the results and run. Submit. Solution is done now. Let's look at the results. This is our geometry, and this whole geometry, and let's look at the changes. In order to look at the changes, I have to activate the initial geometry to compare it, and look at normal to the surface, and this is the initial position. There is no pressure, you can see here. Let's apply the pressure. Our pressure is the maximum in the 25th step. Okay, this is the pressure is 760 megapascal. This is a little bit extended. Let's look at in the scalar point displacement. Let's look at in the total displacement. Is there something? Our system is fixed from this point, therefore the deformation is from left to right, therefore this is gradually changing from left to right, but it is around of 0.02 millimeter. Maybe it is changing in the mid section. Let's look at in the midpoint, I mean this point. Yes, you can see from here the maximum expanding due to the applied pressure is seen in here, the differences, but this is not quite important right now. Let's look at what will happen after releasing the pressure. Go to final step. When we are releasing the final pressure, we can see there is a difference between these two lines, and we can see the plastic deformation. Let's look at this deformation in X component. It's around of minus 0.1 millimeter. 0.01 millimeter, sorry. This is the plastic deformation. And what is the residual stresses on the surface? Look at the scalars. Normal stress. Okay. Now we see some singularities, but we have to make some filtering in the scale. Model plot settings. Let's look at this results, and the residual stress is around of minus 50 megapascal, which means the compressive stresses are seen on the surface. And outer stress component. You can see here the equivalent one meso stress on the surface is around of 450 and 500 megapascal. Okay friends, in this tutorial we saw the autofrettage process and strain hardening effects under the high applied pressure.